This video is a discussion concerning some special discrete random variable. Well, in this video, actually we're gonna only discuss one discrete random variable because it's just so important in practice. Well, we know some discrete random variables, they have very special distributions, they got their own names, and to learn about the distribution, we need to specify, well, for discrete random variable, we only need to specify the probability mass function, which is the probability value of such events, x equal to x for arbitrary small x from the support of the discrete random variable, right? All the possible values could be taken by this random variable. In this video, we have a very special probability mass function. It involves Euler's number, E, and this is the Poisson distribution. And the whole video, we're gonna focus on this specific Poisson distribution because it's so useful in practice and it's applied to everywhere. This video will only discuss a surface of its usage, and hopefully you enjoy this video. Let's start the discussion with the Poisson process, a very simple one. Let's consider the following scenario. We have a web server, and this web server will receive requests from computer A randomly. Well, the question is, how do we properly model the random variable x, which is the number of requests from computer A within a time interval of length t? Right? How many requests this web server would receive from computer A? Well, let's consider the following conditions to simplify. Well, because in order to model something, we always start with some basic assumptions in order to find some parsimonious, simple model that could approximate the scenario we want to work on, right? So here we consider the following assumptions. Let's say the probability of more than one hit in a very short interval is negligible. So at most, you have one request within a very short interval. So it's either 0 or 1. Okay, let's consider how do we specify the probability. Well, the probability of a single arrival in a very short interval is proportional to the length of the interval. So the longer you wait, the more likely you receive this single arrival, and within a very short interval. Okay? And within a very short interval, at least we receive, at most we receive one hit. So as either 0 or 1, and the successful rate should be proportional to the length of the interval. Okay, next thing is the numbers of the hits in non-overlapping time intervals, they are independent. Okay, so what happens in the time interval AB should be independent from what happens in the time interval CD as long as the intersection area is empty. So what happens yesterday should be independent from what happens today, things like that. As long as the time duration, they don't overlap with each other, we assume they're completely independent from each other. In order to simplify the model, we are going to consider. Now, how do we translate those assumptions in formal statistical language or probability language? Let's consider first the two assumptions we want to work on. Right, first, the probability of more than one hit is in a very short interval is negligible. So at most, the number within a very short interval at most is simply 1, right? It's either 0 or 1. And the probability of a single arrival in a very short interval is proportional to the length of the interval. So the first one specify the possible value could be taken by the random variable in a very short interval, right? It's either 0 or 1. The second one specifies the successful rate. We have a Bernoulli distribution, right? So this is how we model this one. The arrival of one request within a very short interval, S plus delta t. Well, it's half open, half closed interval. I will explain later why I use this half open, half closed interval. Based on the two assumptions we want to assume, we suppose those two assumptions work okay in practice? Well, the arrival of one request within such interval follows Bernoulli distribution. Here, we make use of the second assumption, right? The successful rate is lambda delta t, which is indeed proportional to the length of the time interval. And we denote this random variable as indicator function of this time interval. Okay, so it's a Bernoulli distribution either equal to 0 or 1. This one is either equal to 0 or 1, 0 if we have no requests, and 1 if we have one request. And delta t here, we are consider delta t to be a very small number. It's so small such that whatever lambda you choose, the lambda delta t is always, well, as long as lambda is positive, right? So this is always between 0 and 1 because delta t is very, very, very small, okay? Now we have this indicator function. And the question is, we want to model for something of the length t, right? We want to model, here we have what happens within a very short time interval, s plus delta t. So it's of length delta t. And we want to model something of duration t. So for example, I want to model what happens within a day or 1 minute. Those are much larger than the delta t we work on. So how do we proceed from there? Well, let's consider the second assumption we make. The number of total requests within this interval s till s plus t now is an interval of length t, right? Still half open, half closed. It's going to be the summation of all those indicator functions. And here, to simplify the condition, we assume t over delta t is a positive integer. Let's assume this is always true. Now we can think about the second assumption we want to work on. What do you observe about those indicator functions? You can pause the video here and try to infer what we can get for those indicator functions. Look at those time intervals. Well, they are non-overlapping time intervals. And based on the second assumption we want to work on, the number of hits in non-overlapping time intervals are independent. We know those are independent Bernoulli distributed random variables, right? Each indicator function, each indicator random variable here, they all follows Bernoulli distribution with successful rate of lambda times delta t, right? So for the first one is denote the number of requests in this interval, and the second one start with s plus delta t, half open, and then s plus 2 times delta t, okay, half closed. This is the first interval, second interval, third indicator, start with the plus 2 delta t, and till third, 3 times delta t, okay? And we keep going. Then from s, in the end, we have until s plus t. Look at those intervals. Each of these interval indeed is of length delta t. So each of these indicators all follow the Bernoulli distribution of lambda times the length of the interval delta t. They have identical distribution. At the same time, those intervals, they are non-overlapping time intervals. They are independent. So we have IID, the IID indicator random variables. And what is their summation? We sum them all together. Well, we know this follows binomial distribution, which is the sum of independent Bernoulli distribution of the same successful rate, lambda delta t, right? How many indicator functions we have? Is t over delta t, right? Here we always assume t over delta t is a positive integer. Now we have this distribution, okay? It follows binomial with t over delta t, and the successful rate is lambda delta t. However, it still looks a little bit peculiar to have this delta t here, right? Because we assume delta t is an arbitrarily small number. How do we model that? Let's consider a very special case. Let's consider a very special case such that this delta t, let's consider as t over n. N is a positive number. And now we let n goes to infinity. Therefore, this delta t indeed will be arbitrarily small. It will go to 0, right? We are splitting this interval from s to t. We are cut them into finer and finer grade, right? Because now we are splitting in more and more small time intervals here as we increase the number of n. Now we have more and more intervals with shorter and shorter lengths. The question is, what happens to such cases? If this delta t indeed will goes to 0, then what happens to this PMF function? Is it still a well-defined PMF function? Okay, let's consider this limit, right? Let's denote x is the limit random variable. And the probability of x equal to k equals to the limit. Here we consider the special case that delta t is equal to t over n, and we let n goes to infinity. Okay, so we are choosing a smaller and smaller time interval here. And this is indeed a well-defined PMM function. Okay, and it has a very special form over there. Involves the Euler's number E. So how this is done, right? We start with this PMF function of the binomial distribution. Here, given this specification, delta t is t over n, then we have n over here, and the successful rate will be lambda times t over n, right? We just plug in those parameters. This gives the formula here. Next, how do we calculate this limit? Okay, let's expand the binomial coefficient by its definition, which will be n factorial divided by k factorial and n minus k factorial. Okay, and lambda t to the power k times 1 over n to the power k. And here, for the third term, we decompose them into two parts, which is 1 minus lambda t divided by n to the power n, and this 1 to the power minus k. Okay. As for now, we just ignore this part for now. Let's take a look what happens there. Okay. Now we group this term, lambda t to the power k and a k factorial together. That would be this term. And let's group all the remaining terms. All the remaining three terms over there, it will be this product, right? So after we cancel the common terms within the n factorial and n minus k factorial, that's gonna be n times n minus 1 until n minus k plus 1, right? So there will be k terms and divided by n to the power k. There will be n k n's, they're gonna multiply together. So this is the products here. Okay, now we from this formula, we get this one. What happens to the limit if we have n goes to infinity? Well, this one remains the same. This one, if you take a look, k is a fixed number, right? And for each of them, when n grows larger and larger, they are all equal to 1. So there are k ones multiplied together. The second term is essentially 1. And what happens to this term? This term is again, right? When n grows larger and larger, this one is essentially 0. And 1 to the power minus k with k with k as a 0 or positive integers, we know it's still 1, right? This one is still 1. So all the remaining terms will be this one and this one. And the limit of this term is just e to the power lambda t. And what's remaining is lambda t to the power k and divided by k factorial. To deliver the limit of this term, we make use of the definition of the Euler's number, which is, we know we use the fact that the limit here will converge to e to the power x. And in the above case, we know the x is minus lambda t. Okay. This is a very special PMF function, right? So far we have seen nothing involves Euler's number, and this is a very special PMF function. What is a Poisson distribution then? Well, if we denote t equal to 1, x is the number of random requests from computer A with a time interval of unit length. Well, here we set t equal to 1. Then we say x follows Poisson distribution with this arrival rate lambda. And it follows the PMF here, where we simply set t equal to 1. This is the PMF function of Poisson distribution. Now, we discuss some basic properties of Poisson distribution. First, let's calculate its expectation. Right? We can calculate this one by its definition. We already know its PMF function, right? And by the definition of the expectation of discrete random variable, we know it's a weighted sum of all possible values taken by random variable x multiplied with weights multiplied by the weight, with weights equal to the probability value of the x equal to that small x, right? So this is the x, and this is, here is the probability of x equal to x, right? So altogether, and then we sum them together. Now we're gonna simplify this formula a little bit. When x equal to 0, the whole term is simply 0, so we can always start with 1. Now we're gonna move 1 lambda outside the summation, also move the e lambda outside the summation. We move 1 lambda outside. What's left here is x minus 1, and we also cancel the first x with the x in the factorial, so what's left here is x minus 1 factorial. Now, if we denote x minus 1 equals y, now we have x minus 1 equals 0 to infinity lambda x minus 1 divided by x minus 1 factorial. Let's denote y equals x1 minus 1, then we have this formula. And let's take a look at the summation here. Okay, again, according to the property of the Euler's number, we know this summation is equal to e to the power lambda. So the summation here is equal to e to the power lambda, and lambda times e to the power minus lambda times e to the power lambda. These two cancel each other. They're gonna be equal to 1. When they multiply together, what's left is lambda. So the expectation of x is equal to the arrival rate, the arrival parameter, the parameter within the Poisson distribution, which is simply lambda. Here we use the fact that e to the power x can also be expressed by the summation of this infinite series. Okay? And the intuitive result for this one, the intuitive understanding for this result would be, well, lambda describes the arrival rate. Larger the arrival rate, and larger the expected number of the arrivals, right? So it's very intuitive to have such result here, that the expectation of x essentially is equal to the arrival rate, given we are considering the arrival rate within a unit length, right? So it's not a very surprising result. If we consider the arrival rate, suppose we are considering the arrival rate within a length of t, now we can consider the arrival rate for that one will be lambda t, and the expectation of x will be lambda t, right? So this is the very natural result here. We have done the expectation. Next, naturally, we'll consider the variance of this one. So what is the variance of the Poisson distribution? You can pause the video at this moment and try to figure it out yourself. Still, we're gonna calculate by definition. Okay, to calculate the variance, we're gonna make use of the formula that variance of x is equal to the expectation of x to the power 2 minus the average value to the power 2. This formula is true for arbitrary random variables, real valued random variables. So it's also true here. Then to calculate the variance, given we have already calculated this one, so it's always easier to work with this formula. What's left here is to calculate the expectation of x to the power 2. And then we can apply law test, law of unconscious statistician, to calculate the expectation of x to the power 2. We only need to know the PMM function of x. We don't have to know the PMF function of probability mass function of x to the power 2. Knowing the PMF probability mass function of x itself is enough, right? So how do we calculate that? By law of unconscious statistician is equal to x to the power 2 times the probability of x equal to small x, right? And we're gonna sum up all possible values together. This gives this formula. Next thing is, how do we simplify this formula here? How do we simplify the summation here? Again, we're gonna start with 1, because when x equal to 0, then it's just 0. Now we cancel 1x here and 1x in the factorial. What's left in the factorial will be x minus 1 factorial, and here is x. Here is still 1x left, and we have lambda to the power x times e to the power minus lambda. Now we decompose x. We rewrite x as x minus 1 plus 1, right? It's still x. But we can split the summation here into 2 parts. Later on, you're gonna see why we split them into 2 parts. Look at here, right? Now, if we denote x minus 1 equals y, and let's move 1 lambda in front, okay? Let's focus on this first term here. Let's denote, so it's x starting from 1, so x minus 1 starting from 0, x minus 1, lambda. Let's move 1 lambda in front. x minus 1 factorial. If we look at this one, and let's denote y as x minus 1, this is the result we have. And this is exactly the formula we use to calculate the expectation of y, right? Y times the probability, small y times the probability of x equal to small y. Okay, that is the first term, which is equal to lambda times the expectation of x. Okay, let's take a look at the second term now. Well, the second term is here. Again, we move lambda, one lambda in front. We also move e to the power minus lambda in front. And what's left here, if we denote y as x minus 1, is this value. And look at this value. This is according to the formula we just described. This summation is equal to e to the power lambda. So lambda times e to the power minus lambda and times e to the power lambda. These two multiplied together equals 1. What's left is lambda. So now this is the results. We just plug in the expectation of x. We know the expectation of x to the power 2 is equal to lambda to the power 2 plus lambda. So here we are trying to calculate the variance. The last step is just plug in on this formula. We know this is going to be lambda 2 plus lambda minus the expectation of x is still lambda to the power 2. So lambda to the power 2 cancel each other. What's left is simply lambda. The variance is also lambda. This is also a very intuitive result because with a larger rivalries, right? You have more possible different numbers of visits. The variance is also getting larger, right? These are the basic properties associated with this random variable. And we're also gonna discuss some special properties of the Poisson distribution. The first one is from binomial to Poisson distribution, we're gonna introduce a Poisson paradigm. So what is a Poisson? How do we introduce the Poisson distribution to start with? Well, we start with Bernoulli distribution and binomial distribution and show that the limit, right? The limit previously, this is what we have done. We express, we started a summation. We started a summation of indicator random variables, indicator functions, each of them with a very small successful rate, given lambda delta t is a very small, arbitrarily small number. And we started many IID distributed Bernoulli indicator random variables. Indicator random variables, and we sum them together. We're gonna sum many IID indicator random variables together, and they have very small successful rate here because delta t is very small, right? We let delta t goes to 0. Then we have the Poisson distributed random variable. And the successful rate lambda is simply the summation of lambda delta t. Okay, now we can relax the condition a little bit and consider this one. So it's still a summation of indicator random variables, but now we assume we can relax a little bit. They can be independent. They can also be weakly dependent events. Again, we require n is very large, right? Here n is also very large. When we have delta t goes to 0, when we let it go to 0, and pi very small, it can be shown that this x, the distribution of such summation of many indicator random variables, if they are roughly weakly dependent or even independent with very small successful rate for each of them. So each event AI here only occur with very small probability, distribution for such random variables can be nicely approximated by Poisson distribution, with the lambda equal to the summation of all these small p's. This is very useful in practice, especially in actuarial science, because here we are describing something, we are describing the number of occurrence of very rare events. So in actuarial science, it's very useful to use Poisson distribution to approximate, for example, the number of car accidents or health issues, right? Those are rare events. And sometimes if we consider different events, they're roughly independent from each other. And there are many different car accidents, and each of them only happen with very small pi. If we sum of them together and we want to know the total number of occurrence of such rare events, we can use the Poisson distribution to approximate their outcome. So this is the first special property of Poisson distribution. And let's take a look at the second one. What happens to the summation of independent Poisson? Well, it's gonna still follow Poisson distribution. Well, think about the initial idea. How do we model this Poisson? We have a web server, right? Suppose web server not only receive requests from computer A randomly, but also from computer B. A and B, suppose they are independent from each other. Now, how do we properly model the random variable y, the number of requests from either computer A or B within a time interval of unit length? It's exactly the same story. We can even combine, we can regard computer A and B just as one new computer. And again, this new computer is gonna send some requests to the web server. Of course, because now we are combining two computers together, we need to sum their arrival rate together, right? Suppose lambda A has arrival rate lambda A, B has arrival rate lambda B, we just sum them together. And the rest follow exactly the same logic. So indeed, if we have A follows Poisson distribution with arrival rate lambda A, B follows Poisson distribution with arrival rate lambda B, and they are independent, the summation of them will still follow Poisson distribution, but now with different arrival rate, which is lambda A plus lambda B. Well, we can easily prove these results by deriving the PMF function of y, right? Because we know the name, well, we see this one, y follows Poisson distribution, as long as the PMF function of y is exactly the same function for a Poisson distributed random variable with parameter equal to lambda A plus lambda B, right? So let's verify the results and prove the result by looking at the distribution. Now we know to specify here, given A and B, they're discrete random variable, and the summation of them, a new random variable here, y, is also a discrete random variable. And to check the distribution of discrete random variable, we only need to look at their PMF function. So here, let's look at the PMF function. Let's choose one arbitrary k from the natural number is as a 0, 1, 2, 3, and keep going. What is the value here? Okay, now I have already shown the results here, but you can pause the video here and try to figure out the calculation steps yourself. To calculate the probability value of A plus B equals K, let's consider this summation, right? So what are all the possible values taken by B is can either be 0 until K. Because both A and B, they can only take non-negative integer value because they follow Poisson distribution, right? counting the number of requests within a time interval, so they only takes non-negative integer value. And now let's consider this special product and sum them together. What is the intuition behind this summation? Well, we're looking at the summation a and b equal to k, right? If we look at this event, it's essentially equal to all the event of a equals k minus I and b equals I. And all the possible values will be from I from 0 to k, right? Given they both can, both a and b can only take non-negative values. And they are mutually exclusive events, so according to the axioms of probability, the probability of this union will be equal to the summation of the individual probability, which is the probability of a equals to k minus I and b equals I. Now, according to the definition of conditional probability, we know the probability of this joint event, a equals k minus I, b equals I, can be expressed in this format, right? Which is the product of the probability of b equals I with the conditional probability of given b equals I, a plus b equals k. Well, this is also can be expressed as a equals k minus I. So the conditional probability here by the definition here, by the definition of the conditional probability, when they multiply by the probability of b equals I, we know it's essentially equal to the probability of a equals k minus I and b equals I simultaneously, right? So this is the first term here. It might be easier that we write this event as a equals to k minus I, right? It's a equivalent because conditional on b equals I, the event a plus b equals k is essentially the event a equals k minus I. Now, if we consider this conditional probability, what can you say about this conditional probability? We know a and b, they are independent from each other, right? So what can we say about this conditional probability here? If a and b, they are independent, we know given what happens to b, the probability of this event will remain exactly the same. So this conditional probability is essentially equal to the probability of a equals k minus I. Now we know this value, right? It's just a PMF function of a Poisson distribution with successful rate, with a rival rate lambda a, and this one follows similar idea. We can plug in their values, which will be this multiplied by this, right? Now we group them together. We group the e together, and given its constant within the summation, we put it in front of the summation, and we times a k factorial and divided by 1 k factorial, the number remains the same, okay? And what's left here is lambda to the power k minus I and lambda to the power I. So this is the result we have here. And take a look at this. Take a look at this ratio. This is essentially the definition of the binomial coefficient. To deliver the final results, we make use the effect of this binomial coefficient. Identity involves this binomial coefficient. This summation is essentially equal to lambda a plus lambda b to the power k. And if we look at the format here, this is essentially the PMF function of a Poisson distributed random variable evaluated at the number k. So indeed, y follows a Poisson distribution with arrival rate lambda a plus lambda b. Okay. To deliver the final results, indeed, we make use of a results involving binomial coefficient. This is a well-known identity here. And we have a very nice story proof for this one as well. So a plus b to the power k is essentially k a plus b's k terms of a plus b, they multiply together, right? And we know for each of the outcome, if we span the outcome, we know for each of them will have this format with a to the power k minus I and b to the power I, with I from 0 to k, right? So essentially, but how many of these terms we have? So for example, here, if we choose I equal to, for example, 0, then basically means we need to select a in each of these k terms. That's k choose 0, right? For example, if we choose, if we consider how many terms we have of this format, a to the power k times b to the power 0. That means we need to choose how many a's from these k terms. We need to choose k of them, and which means we need to choose 0 of b's from these k terms. So k choose 0 for b, and here is simply 1, right? And what happens if I equals to, for example, 1? That basically means, well, we need to choose 1b outside those k terms. There are k different choices, and the remaining will be 1, right? And the span, if we span all terms together, that will be the summation of all these possible outcomes. We're going to sum them together. So this is a identity involving the binomial coefficient. With the help of that, we can show that indeed here the y, the summation of two independent Poisson distribution, will be again a Poisson distribution. The summation of two independent Poisson distributed random variable will still follow the Poisson distribution, right? Now this is the second special property we're gonna introduce for the Poisson distribution or Poisson distributed random variable in this video. And the final one is from Poisson to binomial. We know to introduce this Poisson random variable, we start with binomial distribution, right? Start from the indicator a random variable, we sum them together, those are binomial, and the limit of the binomial we deliver a Poisson distributed random variable. But now we're gonna from Poisson distribution to show it can also mimic the behavior of binomial distributed random variable. We can consider conditioning. If we have two Poisson distributed random variable and they are independent, conditioning on their summation, they're gonna follow binomial distribution. So now let's reconsider this scenario. If a web server receives total n requests from either computer A or B, So again, the number of requests will follow Poisson distribution, and the number of requests from the computer A will follow Poisson distribution as well. And from B is also a Poisson distribution. Their summation is also a Poisson distributed random variable. But for each, given these two computers are independent, for each signal, we know it could either be from A or B, right? Suppose we receive a signal, it could be from the computer A or could be from the computer B. If we denote the indicator function to be 1 if this signal is from computer A, otherwise 0, then apparently it should follow the Bernoulli distribution, right? So here, let's denote the fact that we have received a signal, and the S signal is from the computer A, because computer A and B, they are independent. They apparently follow the Bernoulli distribution. And the successful rate, well, it's natural to figure that out here. We're going to show later, but it's natural to think the successful rate will be the ratio of the arrival rate, right? If the arrival rate is larger for computer A, then apparently it's the signal for each signal, it will be more likely to be from the computer A, right? And vice versa. So suppose now we have n signals in total, conditional on that information. Suppose we receive n requests already, and we want to know how many from computer A, then we basically sum all those Bernoulli distributed indicator random variable together, right? From 1, this is the S signal, belongs to computer A, then we're gonna sum up I from 1 to n, because we have n requests, and the result's gonna be binomial distribution, right? Sum of Bernoulli distribution, if they are ID, with the same successful rate, we're gonna have a binomial distribution with parameter n at successful rate equal to this value as well. So this is the formal language in probability theory. We just summarize what we have already discussed. If A follows Poisson distribution with lambda A, and B follows Poisson distribution with arrival rate lambda B, A is independent from B, A and B, they are independent, then the number of requests from computer A, given we have received n total requests, the number will follow a binomial distribution of n, where we're gonna sum those n Bernoulli distributed indicator random variable together, right? So they're gonna be binomial distribution and with the same successful rate. Again, to prove this result, we only need to verify the distribution. And given this is, again, a discrete random variable, we only need to look at the PMF function, right? So what is the probability of we have k requests from computer A given the total requests from A and B equal to n? Now let's delete these results first. You can pause the video and try to figure out the solution yourself. How do you prove by showing the PMF function? Okay, let's show the results here. Essentially, we're gonna deal with this conditional probability, right? This is the event we know is already occurred, conditional on this information, and we want to know the number of requests from computer A. The first equation is by the definition of conditional distribution. This conditional distribution will essentially be the ratio of this probability of joint distribution divided by the probability that we know total requests equal to n. A and B, they are independent from each other. Independence means products. So we know the probability of this joint event is essentially the product of individual probability. So the P A equal K, at the same time B equals N minus K is equal to, that number is the same number as the product of PA equals K multiplied by the probability of B equals N minus K. Now we have A, B, and A plus B. We know those three random variables, they all follow Poisson distribution with different arrival rate, of course, but we already know the PMF function of Poisson distributed random variable, right? So we just plug in the value here and here. Now we can, e to the power lambda A, e to the power lambda B will cancel with the term here. And essentially what's left is the factorial, k factorial, n minus k factorial, n factorial is over there. Let's remove it. And we have lambda k to the power k, lambda b, lambda a to the power k, lambda b to the power n minus k divided by this term. Well, this lambda a plus lambda b to the power n, we're gonna decompose it as the two products, which is lambda a plus lambda b to the power k, and multiply the lambda a plus lambda b to the power n minus k. And this one combined with lambda k, this one from the denominator combined with the lambda k to the lambda a to the power k from the numerator contribute the first term. And here lambda b to the power n minus k divided by the second term is the second term here. Now let's take a look at a close look here. Right, this is the successful rate. This equals 1 minus of this successful rate. And this ratio here is essentially n choose k. This is eventually a PMF function of a binomial distributed random variable with n total n draws, total n requests, and the successful rate equal to lambda a divided by lambda a plus lambda b. So indeed, the number of requests from computer A given this information follows a binomial distribution. So this video discusses many materials related with Poisson distribution, and we start with binomial distribution to introduce this Poisson distribution, and we end with this binomial distribution. Right? From Poisson, we can also deliver the binomial distribution. Hope you enjoyed this video, and thank you for watching.